in real life problems. So let's look at some of the introduction that I got from the textbook. So rates of change. So when we measure the gradient to a curve, is measuring the rate of change. So let's see how we can do that. So far differentiation has been developed geometrically in terms of tangents to curve, and many more geometric ideas will be involved as calculus is developed. Calculus has many interpretations. However, it has always been a very practical subject. It is an essential part of engineering, economics, and all the sciences. This section will begin to interpret the derivative as a rate of change in various practical situations. Some variable quantity q is a function of time t. So we're accustomed to use the polynomial like y in terms of x. Now we can use more y in terms of x. Instead of using y, we could have q for quantity, t for time. Differentiation with respect to time will give the rate. So when you differentiate with respect to time, it becomes the rate at which the quantity q is changing over time. Two important type of rates are velocity and acceleration, but we have these are in the 11 course. However, Cambridge have decided, like the old syllabus, that will leave the discussion of motion until year 12. Whereas some school may do it in year 11, but we're going to do it in year 12 because motion requires a great deal of more theory. A couple more of questions in the next exercise, however, indicate how velocity and acceleration are particular types of rates. Okay, next one, we're going to look at average rates and instantaneous rates. Okay, so again, what the question comes, why is the rate? Because if that's a quantity, let's say kilogram, and that's in minutes, so the rate will be, remember in year 8, rate compares two different quantity, like kilogram per minute, right? When do the rate. Okay, so as an example, so suppose that quantity q is given as a function of time t. There's a thing. There are two types of rate. Let's examine these two types. First is the average rate of change, which corresponds to a chord. So average chord, so there's 1 point, t1, t2, which correspond to quantity 1 at time 1, quantity 2 at time 2. If we join these two dots, we get what we call a chord, as we know earlier. So there's a chord, and that represents the gradient of that chord represents the average rate, because the gradient is rise over run. So the rise is q2 minus q1, and this is t2 minus t1. So the average rate is the difference of it's like y2 minus y1 over x2 minus x1, but we don't do that, right? So it's y2 minus y1, that's the gradient. But that's like a very theoretical. Now apply to the context of rate, that is more useful. Or in other words, it's a change in quantity, misspelled, sorry. Quantity over change in time, right? Okay, so that's the gradient. So remember that as a formula. That's called the average rate. We also have what we call the instantaneous rate, which corresponds to a gradient of the tangent. This instantaneous rate of change at time t1 is dq dt at t1. So that's the gradient of the tangent, right? So that's the instantaneous rate, which is dq dt, right? So instantaneous rate is dq dt, or you can think of it as the limit as delta t approaches 0, changing q over changing t, just like this one, and that becomes the derivative, which you evaluated at t equal to t1. So you want to find the instantaneous rate at the time 1, you substitute, right? This is the alternative notation to the fx notation. If f dash of ft, that's the rate, that's the quantity, and q dash is f dash of t, but the function notation will make it clearer where we substitute t1 in to find the instantaneous rate. Okay. All right, hopefully it's all clear. Hopefully, again, it will be clearer when we do an example. We'll do 2 examples, I think. 2 examples, and then we'll discuss other things about derivative that will unlock more information. In many problems, it is useful to sketch two graphs, one of the quantity Q as a function of time t, and the other rate of change, dq dt, also as a function of time t. The quantity Q is usually replaced by a more convenient pronumeral, such as P for population, or V for volume, or M for mass. Take particular care to use the correct units for the quantity in time, the time, and the rate in final answers. Okay, so we don't have to always use Q. It could be P for population, V for volume, M for mass, whatever. So it doesn't always have to be Y. And take particular care to the correct units for the quantity, the time, sometimes could be, and the rate in the final answers. So again, that will be discussed in the next example. All right, let's look at this example again, straight from your textbook. A cockroach plague hit the suburb of Birrawong last year, but was gradually brought under control. The council estimated that the cockroach population P in millions T months after 1st January, which is given by that. So remember, P is in million, not one cockroach, million. So when P is 1 means 1 million, P is 2 means 2 million, and T is in time, not in seconds, not in minutes, not in hours, it's in months. So be careful of the units. And remember, this is when T is 0, it corresponds to 1st of January. So again, this is application of calculus. So we're going to use the equation, but now we have to be very conscious what each pronumeral represents, because if we are not conscious of that, the answer will make no sense, right? You need to be able to interpret the answers. That's how we apply it. I mean, maths can be very theoretical, but once you put it in context, it will mean a lot of things. So we're going to look at A, differentiate to find the rate of change dp dt of the cockroach population. The first question, probably 1 mark in the exam, easy, differentiate. Who can't do that after such a long course on differentiation? So dp dt equal to, it's important to write dp dt instead of p dash, because clearly you're differentiating in respect to t. So the answer will be 6 minus 2t. All right, pretty straightforward, nothing exciting. Okay, now we're going to do part B. It says, find the cockroach population on 1st of January. So again, do one thing at a time. So we're going to find P. We're going to find P, the value of P, when 1st of January, T0, and the rate, dp dt, when T0. And the rate of the population was increasing at that time. Okay, so we have to do two things. Again, read the question, highlight or underline, whatever you do. So let's try this. So P equals to 7 plus 6t minus t squared. And dp dt equals to 6 minus 2t. We'll get these two, and then we have to find out the value of the population as well as the rate at the given time t equal to 0. So we're going to substitute t equal to 0 in both formula. And that will tell us different information. So if I substitute t equal to 0, I will get 7. What does 7 mean? Means 7 million what? People? No, cockroaches, right? So now you have to be very conscious of the units, because we are now interpreting things. And it's only useful if you know what it is. Just like I write that. What does it mean? 5 people, or $5? Again, you need to put the correct units. So math can be too theoretical, but if you are careful about it, it can be very powerful. Okay, let's substitute t equal to 0. That will be 6. What does it mean? 6 million cockroaches. That was the rate of increase per month. So at the beginning, that's the rate of increase. That's the rate of increase. So it's increasing pretty fast. In the first month, after 1 month, you expect to have an extra 6 million cockroaches rate of increase. Okay, so now it gets a bit harder, but it's not harder mathematically. You just have to interpret what you're writing. Okay, that's done part B, and now we're going to do part C. When did the council manage to stop the cockroach population increasing any further? And what was the population then? Cool. So there's a few things. When did the council manage to stop the population? So what's the value of P? Actually, it's not even P. Stop the increasing any further. So it's not about the quantity. It's about the rate, isn't it? That's it. The rate of change has to be equal to 0. So again, it's easy to differentiate. It's easy to substitute. But what do I do? It's easy to kick the soccer ball. It's easy to headbutt whatever, the soccer ball. But when do you headbutt? When do you kick the ball? Like, really depends, right? Otherwise, we could just program a robot. Let's go compete at the World Cup. Yeah? So it's a bit different. But they did program a thing that do the chess. I think he ended up winning the Grandmaster. I don't know. Or maybe got beaten. I don't know. Like, but chess is a bit different. But physical education is more complex. You need a robot that's impossible, right? Almost impossible now, but it could be the future. Could be. And what was the population then? So you have to find the time when the PDT is 0, and what's the population then? Interesting question. Well, we can answer it with the power of calculus. So again, let's write down our equation. The dp/dt was 6 minus 2t. So we have to keep reminding ourselves what the equation is, and we're going to use it for our advantage. So firstly, we have to work out the time when the rate is 0, right? So we're going to go 6 equal to 2t, t equal to 3. Again, what does 3 mean? 3 seconds? No, 3 months. And more specifically, which month would that be? March? No, actually 1st of April. Count your fingers. Try it. Let's try it. T is 0, 1st of Jan. So it can get complicated. 1st of Feb, 1st of March, and 1st of April. Easy for some, hard for some people, but whether you find it easy or not, or hard, you have to learn it. Does that make sense? So it can be difficult, right? 1st of April. Okay, cool. So in 1st of April, it will stop increasing. Hopefully it's not April Fool, but anyway, we'll move on. And then we go, okay, P equal to that. What's the population then? Probably has already gone very big. So let's try. 7 plus 6 times by 3. 3 months. After 3 months, what's the population cockroach? You don't want to go to that suburb, but I don't know. Is it? I think it's a fictional suburb. Well, how many? 60 million. If I get a buck for each cockroach I kill, I don't need to. But anyway, let's move on. A million cockroaches. Roaches. Oh, you could call it roaches. All right. Yeah, cool. That's it. Okay, that's all we have to answer. Oh, we've got so much space. Next page. Okay, now it's going to get exciting. We're going to eliminate the cockroach. Where would the cockroach finally be eliminated? Is that a question about P or dp/dt? P. And what's the value P? 0. Eliminate it. Yes. Let's get rid of cockroaches. All right, what's the equation? Oh my God, we get to solve a quadratic equation. Hopefully you haven't forgotten after differentiating for so long. Oh, I don't need to solve quadratic. Yes, you do. Yes, you do. Quadratic is on the reference sheet. There's a formula there, but I prefer factorizing because it's cooler. And it's actually easier to factorize than to use the quadratic formula. So t equal to -1 and 7. Can t be negative? No, why? T is time, yep. Because we start examining the number of cockroach in 1st of January. I mean, you could interpret that as 1st of December, but we haven't started charting the number of cockroaches before then. So therefore, anything before that will not be used. So we only look at things afterwards. So when would it be finally eliminated? So it will be after 7 months. After 7 months, which is when? August, right? 1st of August. Because January is 1, right? It's not 0. That's why we have to add 1, if that makes sense. Other way around. 1st of August. Yeah, January is 0, yeah? So that's why you have this adding 1 effect. Okay. 1st of August, we'll see cockroach on, oh, we're in August, so we don't see much cockroach anyway. Because they're probably dormant or whatever. Yeah, it's pretty cold last week, so that's good. So do not eat food in your bedroom because you will attract unnecessary insect in your room. I know, I'm sure you know what I mean. Okay, all right. All right, what was the average rate of increase in the population from 1st of, average rate. Have to remember. Now, the average rate is equal to P2 minus P1, right? Instead of Q. So we have to work out the time. T1 is 1st of January. T2 is 3, not 4, April. And that will be P1 equal P2 equal. So you have to work out, so we have to quote the formula. The formula was 7 plus 6t minus t squared. Substitute 0 in, get 7, substitute 3 in. I think we got the population at this time as well. 16, we did it before already, right? But if you forgot it, you've done it, you can do that again, doesn't hurt. And then we'll do 16 minus, notice that I write down the formula first to eliminate careless error. So what would that be? 16 minus 7 is 9. So it's 3, is it months? No, will be 3 cockroaches, not 3 cockroaches, 3 million. 3 million cockroaches per month, right? So you can think of it's true, right? So we on average, you're expecting to get 3 million cockroaches per month. So because it starts from 7 to increase to 16 over 3 months, means every month you expect 3 extra million cockroaches. Although at the beginning, our instantaneous rate was 6 million cockroaches per month. So at the beginning was increasing a bit faster. But we'll look at the graph to understand what I just said. All right, okay, so let's try that. So I've got the graph for you, and we're going to do some analysis of that. And if you know how to analyze the graph, it's going to be easy. Cool? Okay. Draw the graph of da da da, do do do. Okay, pretty easy. Now, let's write it down. P equal. Now, you can use all this information. You don't have to go, oh, I have to draw a parabola. Like, you can just still use the information that you have, which is 6 minus 2t. Is it 6 minus 2t? Okay. Now, remember the initial number of cockroach was 7, and after 3 months, it becomes 16, right? So that will help you to graph it against time. And you know it's a parabola, and in particular, it is concave down. And it got eliminated after April, after August, which is 7 months. So you have this graph already that you don't, oh, do I have to factorize and that? Well, you can just use the information we have. Got eliminated, right? Eliminated. So eliminated. Okay, eliminated. And this one is when you stop increasing. So it must be maximum, where the tangent is greater than 0. dp dt is 0. So we have all this information, and that's the initial quantity. Pretty cool, right? So my suggestion is you look at the previous part to help you to draw the graph. You don't have to go, oh my god, parabola. Do I have to find x-intercept, y-intercept, go through the whole procedure? They've already gone through the whole procedure already. Okay, right. So how about the line? You should draw the line. Again, I have deliberately included the graph of derivative underneath the quantity so that you can see the connection between them. So derivative 0 at 3, right? At 3. I use a highlighter. At 3, this one, actually yellow, right? At 3. So 0. So it's going to be greater than 0. What was the initial rate? 6 million per cockroach per month, right? Remember we got that in part B, right? That's part B, right? That's 6 million cockroach per month. and then the rate decreases to 0, and then after that it keeps decreasing, and then the graph actually stops because there's no cockroach. It doesn't go down, right? It can't have negative cockroach. Or you could maybe ghost, cockroach become ghost, I don't know, but it just doesn't make sense, right? So make sure your graph, so usually when you draw parabola, it goes on forever, but in the context, it doesn't go on forever. We'll just use it to model certain parts, right? So we're going to go almost finish. So we have to draw a straight line connecting over here, and you have to stop there. You can't draw an arrow because it doesn't go on forever. Yeah. So we use it to chart from the beginning, 1st of January, and then August got eliminated, and then stops. Yeah. Okay, cool. Any question? So it's quite interesting. Maths, Isaac Newton, applied calculus to physics, but biology, many things, economics can all use mathematics. And yeah, so that's like a biological problem, biology. So a lot of maths involved. So yeah, people say, oh, biology is a lot of terminology. Yeah, but that's part of it. But it can be very mathematical. Okay, now we also have to show, add to your graph the tangents and the chord. So the gradient of the tangent is 6, right? Gradient, that's the gradient of the tangent. That's 6, right? dp dt equal to 6. That's when t is 0. If that makes sense, I've substituted 0 into derivative of 6. What's the other one? What's part C? Part C will be, that's when dp dt is 0. Yep. So I've shown that. Okay, that's good. What else have to show? It got eliminated. Eliminated. So that's when the quantity is 0. Right? Quantity is 0. Eliminated. When p is 0. Get the idea? What else have to do? We have to show the tangent and the chord. So the chord was the average rate. Notice the average rate from 0 to the April. So this is 1st of April. This is 1st of Jan. And the gradient of the chord. Now notice that average rate is less than the instantaneous rate because at the beginning it's increasing very fast, but then it stops after 3 months. But the average rate is just 3. So the average rate equal to 3, right? 3 million cockroaches per month. So it's the gradient of, that's the chord, right? That's the chord for the average rate, tangent for the instantaneous rate. Before we finish, we also have to have some analysis, which is on from the textbook. We can see from the left-hand graph that the cockroach population was increasing when, forgot what word, when something has what? When something, every tangent to the left of t equal to 3 has something gradient, has positive gradient. When something, when the dp dt is positive. Is that, maybe that's every tangent to the left of t3, right? When t equal to 3, the left of it is positive, right? It's increasing. And on the other hand, between 3 and 7, the cockroach population was decreasing. Every tangent to the right of t equal to 3 has a negative gradient, right? It's decreasing. So if the, seriously listen, if the derivative is positive, it's going up. If the derivative negative, is going down. So we have a physical interpretation of that. At t equal to 3, the cockroach population was stationary. That is, it was neither increasing nor decreasing, and the tangent is horizontal, as shown in here. These 3 words are used throughout the calculus to describe functions, whether or not a rate is involved. So stationary, decreasing, and increasing. Right? So I'll maybe highlight this. We're going to use this a lot in our discussion about calculus, stationary, decreasing, increasing, right? We're going to use that a lot. And it doesn't have to involve the rate, but in the context of rate, it makes it more, you'll find it more straightforward to interpret. All right, that's done. So we've done 2 pages. I think maybe 3 pages so far. We've got 1 more question, then we're done. Okay, about this question. All right. So we have to interpret the graph. Increasing, decreasing, stationary. What we just said are now summarized in this box, highlight it, or maybe draw a box around it. So this is summarized what we just said. So suppose fx is defined at x equals a, with f dash of a also defined. If f dash of a is positive, that is if the tangent slopes upwards, then the curve is called increasing at x equals a. If f dash of a is negative, the tangent slopes downward, then the curve is decreasing at x equals a. So again, give you a picture. So that increasing means the tangent slopes upward. This is decreasing, tangent slopes downward, right? And if the tangent is horizontal, means that like this, right? Or it could be a different picture. Anyway, up to you. Okay, cool. Now I'm going to use some of these ideas to do the next question. Example 35. The graph, again, that's straight from the textbook. The graph on the right shows the temperature T of a patient suffering from Simon syndrome. Don't know what that is. Some of you may know. A time T hours after her admission to hospital at midnight. So that immediately you know midnight is 12 a.m., right? When did her temperature reach its maximum? When? Will be at that will be 3 a.m., right? All right, 3 a.m. And when was her temperature increasing most rapidly, and when was it decreasing most rapidly? So increasing rapidly means what? Means the gradient is steepest, right? Steepest. And steepest is characterized by, so I think increasing most rapidly will be at the beginning before it becomes stationary, and decreasing most rapidly must be at this point. Later on, we'll learn this point to be called the point of inflection. But now just remember, this is like decreasing most rapidly, right? This is less steep, right? That's almost flat. That's almost flat. So that's decreasing most rapidly. So we would say increasing most rapidly at at 12 a.m. Increasing most rapidly. And decreasing most rapidly, that will be 6 a.m. if that makes sense. Hopefully it makes sense. So again, just interpret like most steepest, right? That's positive steepest, that's negatively steepest. And then what will happen to the temperature eventually? What's happening? It's reaching an asymptote, right? So what does it mean in terms of modern day language? Yeah, or maybe normal, maybe we can say the temperature is stabilizing. Is stabilizing, right? Stable, or possibly normal, but we have no scale here, right? We have no idea what the temperature is, but it's getting to normal. So it's stabilizing. How do I spell? Is it stabilizer? I? Yeah, even though it's I, it's pronounced as stable. That's why it's very hard to speak. And American like Z, but we do S, and England stabilizing. Yeah, but if you do spell check, make sure in Word change it to Australian or English, and then if you change to American, they always underline it. You say what's wrong because it's Z, and then say yeah, get the idea. And if you use Word, stabilizing. Okay. All right. Now we have to sketch. We have to do some sketching. Sketch the rate, right? Now in the previous example, we have a formula to help me, right? I have a formula. It's a straight line graph. But notice that if you look at this more carefully, that the stationary point corresponds to an x-intercept of the derivative, and if the graph is going up, the gradient derivative is positive. Graph is going down, derivative is negative. And that's all we have to know to do the next question. Let's try it. We're going to draw the graph of the derivative. Have a try, and you have some questions that just to get you to think about it. T dt dt, right? But one's capital T, one's a small t. Okay, so we need to label this information, right? So let's use the dotted line, right? You will see that it has to, then you see the correspondence. Now, certainly, we will see that the gradient is 0 at 3. 0 at 3, right? That's 0. Gradient 0. However, on the right, on the left of 3 is increasing. The gradient is positive. On the right, the gradient is negative. So you expect that your graph, again, I will use a highlighter that's going to be, maybe use a color here. It's going to be positive. Actually, that's a bad color. Actually, maybe, all right, doesn't matter. Okay, Control Z, Control Z. Let's try again. This corresponds to positive, somewhere here, right? Positive. And here will be negative, somewhere here, right? So now let's try to draw the graph. Again, there's no way to tell where to begin, but it's got to be somewhere here. So the gradient is something positive number, not too small, so somewhere here, right? And then it's going to reach 0, right? And then it's going to be negative. After 0, negative. And then be careful that the gradient approaches 0. But be careful at 6, remember the gradient was maximum, was the most negative. So after this, it should go up. So after this point, it should go up because that's the most negative, and then approaches 0. Right? Because that's when it's decreasing most rapidly. That's decreasing most rapidly. And the most rapidly will correspond to the lowest point. After that, it will start to slow down, but then the gradient approaches 0. dp dt approaches 0 because the gradient is getting flatter, the tangent is getting flatter, and that's the increasing most rapidly. Most rapidly. Again, I would suggest you to annotate and have an understanding in the correct interpretation of what it means. And that's when it stops increasing. Stop increasing. So it's increasing, but slowing down, stop increasing, and then start to decrease. And then decreasing most rapidly, and then start to go back to 0. And it's like a movie, beginning, climax, and then finish, resolution. That's good. I think we've done. So again, understand this, and then try to do a question in the textbook 9J today. Exercise 9J. Start now. If you are not up to date, I suggest you do that today so that you still remember what I told you. Start now. Thank you.